Alright, so as you can see, I've already written down some equations. For this problem, using the approximation, the integral of a function, if the interval is small, the interval of integration is small, then it's just the value of the function at the starting point or midpoint or wherever times the width of the interval. Estimate the fraction of nitrogen molecules at a temperature of 300 degree Kelvin that have speed between 290 meters per second. Okay, so what this approximation is telling you is the following. Okay, what this approximation is telling you is from V to V plus epsilon naught FV dV. So you know that is so this is a function. This area is FV1 times height. That's what this is telling you. The integral is this area, and that area is the height of this column times the width of this column. The height of this column times the width of this column. Okay? So that's what it's telling you. All right. Now we have the Maxwell's-Boltzmann distribution. The Maxwell's-Boltzmann distribution tells you the probability of a molecule having a certain speed is a function looks like that, and this function is given by that. That's the probability function. Here is PV. Okay, and you see the probability function dV integrated over all speeds is equal to 1. So this quantity is dimensionless. PV dV is dimensionless. So this has units of 1 over velocity, 1 over speed times speed. That's dimensionless, and you add all those pieces up, that adds to 1. Okay. So PV dV, there's that. dV is 1 meters per second. 290 meters to 291 meters. So 291 minus 290 is 1 meter per second. We will evaluate this probability function at V equal to 290 meters per second. All right, so that's what the problem is. So, okay, so we will employ a trick here. Okay, and the trick is the following. In this probability function, this is the mass of a single nitrogen molecule divided by the Boltzmann's constant. And the mass of a nitrogen molecule is 10 to the minus 27 kg, some factor times that. We don't want to deal with small numbers, so what we'll do is this ratio is equal to the mass of 1 mole of nitrogen divided by the gas constant. So wherever we have this ratio, we'll replace this by the molar mass divided by gas constant. Okay. So actually, since there is almost enough space, I will write it right here. Has, and now M stands for molar mass, V square e to the power minus molar mass V square by 2 RT times 1 meters. Okay. And that's what we want to evaluate. So the fraction of molecules with speeds between 290 and 291 meters per second. So essentially, at what temperature? 300 degree Kelvin. So we're asking what fraction of, in this, the temperature in this room is 300 degree Kelvin. What fraction of molecules are traveling between 290 meters per second and 291 meters per second? Okay. Do you guys remember what is the average speed of the gas molecules in this room? Average speed is roughly about 500 meters per second. We're asking what fraction is between 290 and 291. Okay. All right, which is that expression there? We will, okay, so now let me copy that and I'll bring it over. All right, now let's evaluate this. So the molar mass of nitrogen molecules is nitrogen is 28 grams. The mass of 1 mole of nitrogen gas is 28 grams. So 28 into 10 minus 3 kgs. 2 R is 8.314 joules per mole per Kelvin. And T is 300 degree Kelvin. All this to the power of 3 halves. V square is 290 meters per second square. E to the power what I'll do is I'll calculate, oh, okay, got 40 into 290 square, and I'm not going to put the units, 8.314 into 300, okay, so that's what we are calculating. Okay, here is the first factor, 2.26. Here's the second factor. There's the third factor, which is that. And now let's calculate the exponent. So the final factor is oh, 40 into 10 minus 3. I need to put a 10 minus 3 in there. So that's 0.204. Okay, so the exponential factor is 0.509. Those are the various factors. So let's calculate this. So that's 10 to the minus 3. Okay. Okay, what this number means is this is the fraction. So what this means is 12 out of every 1,000 molecules, 12.7, 13 out of every 1,000 molecules has that speed, 290 meters per second. Has the speed between 290 and 291 meters per second. That's what we've calculated.